My name is Musa Yash. I'm from Chicago State University. On behalf of Chicago State University and our Center for Information Security Education Research, we are really thankful for Dr. Safwan Wshah from University of Vermont for accepting to be our host today for our end of the semester webinar, last webinar in the semester under our NSF funded project, which is about building capacity around AI at Chicago State University and its community. Dr. Shah is coming to us with very good experience in the area of AI-powered geospatial analysis, and he will cover several aspects related to his research and his lab. Again, thank you, Dr. Shah, for your time, and we'll be having this for around 45 minutes. He will be presenting, and then we'll have room for Q&A after that. Dr. Shah, the floor is yours.
Thank you. Thank you very much, Dr. Musa. Can you hear me very well, everyone?
Yes.
Okay, excellent. So first of all, I would like to thank Dr. Musa and Dr. Black for inviting me. That's a great opportunity to be here and to share with you my research and hopefully some of our products that hopefully will benefit the transportation departments as well as transportation field. So today we're going to talk about those advancing transportation assets by recognizing them through like AI-powered geospatial analysis. I am Safwan Wshah from University of Vermont. I am associate professor there, and I am a co-founder of Maplyzer company with a colleague named Wasim, and that is also a connection how I end up in here to present this to you guys. Away from what my definition is, what exactly I do, we intersect both machine learning theory and application. I am a guy who have more kind of trust in the application and drive science toward a certain application more than just doing some theoretical answers that maybe end up on the shelves without being used. And what is our core in University of Vermont that we do is geospatial understanding from ground, aerial, and satellite images. That is what we are trying to do. One big theoretical questions. Again, I'm not trying to throw a theoretical questions, try to answer them and put it in the shelf. We try to find some sort of applications and I can connect the dots later on. What we are trying to answer in here, if you have an image, where this image on Earth has been located just only from the visual information. Nowadays, you can just drive your car, you have your cell phone with you, and you connect to the satellites and you can localize your location based on this GPS location from a certain number of satellites signals, and you can actually localize or locate your location. The issue with this GPS, sometimes does not exist in certain areas. Sometimes it's noisy, especially in urban areas, whereas, the very big buildings and the signal will be scattered and the GPS will be really with high error. And also GPS in general, even in a good conditions, with good regular conditions, it might be plus minus 5 meters. So that's a lot. So one alternative that comes from the computer vision field saying, if you have an image just from the visual information, can you localize where it is on Earth? And that is actually a big field that's been actually sparked for maybe 20 years so far. And we are been working actively in this field. My lab is on and off. We are the top in this. We are the state of the art. Maybe one year and the other year, maybe some other group and so on. But we are very well defined in this area. So how you can answer this question? You can, because we just need to localize it based on vision information, just image to image. You can just have the query image where you would like to localize this image, for example, and you can already store a predefined images for this, this location somewhere in a database, and you can just do it as a retrieval problem. That is one solution that people actually defined it long time ago as a retrieval problem. But there is a lot of issues if you would like to do ground to ground image retrieval thing. So there is elimination, there is weather variation, there's temporal changes, there is temporal resolution, viewpoint and camera, you can occlusions and blah, blah, blah. There is tons of problems. But one idea that's one time has been actually proposed and seems like to be really working well. Satellite images already geotagged, already georeferenced. Why we don't just go and have any ground image and say like where this has been taken, we already have all those georeferenced satellite images. Why we just say this image is actually belong to this satellite image? Which is really nice because we have all these satellite images, but there's problems, which is the drastic view changes. This one is a 0-degree image, and the satellite images, they are 90-degree images. So how you can imagine this transformation between 0 degree and 90 degrees and align them and say this image is actually correspond to that satellite image, that is actually kind of a problem. That is where AI can help in doing this kind of a smart transformation implicitly or explicitly by associating the objects and like kind of any kind of sort explicit or implicit features between the two views and say this is the same image. They could be actually captured at different times of the year and also different object resolution, and also could be on the ground you can see cars and so on, but you don't see them on the satellite image. There is some object that's already omitted and so on. So this actually, to answer this kind of problem that we've been working on for many years in my lab, we bring this kind of science from all this kind of knowledge we accumulated to answer this question. This question is, can we, given any sort of geospatial area, and try to combine different views from satellite, from aerial, from ground, as well as not just necessarily those information, can we engage textual description, GIS maps, and more, any information that can help in localizing or understanding that geospatial area and studying it. So that is actually the core science in my lab, and the technology arm, which is Maplyzer LLC, that is what we try to answer such kind of hard questions there. So what we do in our lab very quickly, then we can jump to the main topic today. For example, like what we introduced in our lab, saying instead of doing an image to satellite, what about like, because we take on the ground, we take typically a sequence of images. So what we are trying to say in here, can you do a sequence geolocalization instead of image geolocalization? That's what we introduced. And that's actually been boomed as a field, saying doing sequence geolocalization, we call it. The other problem that existed already in the field, which is if you train a model in New York City, and by the way, the models that we train in New York City and big urban areas, it's actually doing really well. It's doing like maybe 96, 97 accuracy. You can be surprised actually, because really kind of visual information tell you the exact location based on this kind of cross-view geolocalization between ground and satellite images with this really high accuracy on the same city. The answer is yes. Actually, nowadays it's been reached to 99% accuracy. But if you take the model that's trained on New York City and you take it to Chicago, for example, it's going to fail by getting, for example, like 96% accuracy. And actually, before our GeoDTR kind of approaches, the accuracy was reaching around 40, but our GeoDTR was pushing it to around the 60, 63 kind of for cross area. So the question would be how we can train a model that does not overfit a certain region and look at those kind of explicit associations between two views. If we can reach to that point, then we are actually training a very good algorithms that really doing the job no matter where on earth. And eventually what we can do, we can introduce a model that do like a vision GPS that can work at anywhere on earth. And that's what we hope for. And the next one, the next research that we've been doing, and this kind of sort interesting research, can you map the ground image to a satellite image? Can you generate the view of the ground on a satellite image with the help of GIS maps, with the help of OpenStreet maps, GIS information, can you put those in there and generate kind of an open, can generate that aerial image looking there? What's the application? Tons of applications, but just imagine that you have a smart city and there's many cars driving the city. Can you form that aerial image for the city from many images that's been, or many cameras that's been collecting those images across the city? That is what we are hoping for, to generate those kind of aerial images. But this is a long objective that we are looking for, but that academic research can reach to that point at some point. And like the next question is, we already have the GPS information. I'm driving my car in a city. I already have the GPS, but it's noisy. Can you localize my location accurately? That's what we call fine-grained image localization. There is a field called fine-grained image localization that we are working on, and we are trying to get some results with what we call GeoFlow. This is a flow-based match approach where you can start at any point and hopefully you can land to the right location. More interestingly, what we are doing in my lab as well, can you, from a text description, just pure text, can you localize your location? Instead of image to satellite mapping or localization, can you do text to a satellite image retrieval problem? Now this is what we've been working on recently, and we achieved some sort of really good results, 60% accuracy. So someone in Uber is driving, is trying to localize the client, saying the client, I am actually in this location, and start to describe it from the text. The Uber driver can localize the client. So that's very interesting and has many applications. And it is kind of a research, but eventually I would like to go back to to this vision. Can you get as many as information from different views, from different modalities, from different maps, and you have a better understanding about that geospatial area? With that being said, today's research is about object generalization. The question that we would like to answer, suppose that you have an image and that image GPS location is assumed to be correct. Now, where those objects inside that image, where the location for those objects on the map, can you answer this question? So that's what we try to take part of our science and part of our theoretical research and try to answer questions that will be hopefully beneficial to transportation departments. So, and we can claim that we are a little bit leaders in this kind of specific field, and I can talk more about it, which is the sign localization. If we can, the question would be, if you have a bunch of signs that is already captured in the street images, can you localize those signs on the map? That is actually kind of the question that we are trying to answer. So first of all, you need to detect, classify, and localize every single sign from its location on the images and localize it on the map. And try to produce the GIS sign map as an output and try to give some sort of a solution that you can play with. You can zoom in, you can click on the sign, you can see it on the images and so on. You see it on the the sequence of images that you already have, and try to create some sort of interaction between the user as well as the AI that's been localizing those and images or signs on and also that's already participating in the detection and tracking. Motivation, there is transportation departments, they have tons and tons of signs in their on their roads, but they don't really know how many of those already existed. They lost the track, and if they want to do with this the tracking for those signs, they need to do it manually, and that is very extensive labor. They need to do it per every single segments in their road assets, and that's going to be a problem. Luckily, those transportation departments already having trucks and to collect images from streets every year, so they can use this information for maintenance, tracking their assets, and so on. And we can use those images to extract the signs and localize them on the map. There is a large data set also can be extracted from this work to benefit academic research as well. But also there is tons of challenges in this field. For example, like there is a huge number of images to be collected. There is a large number of sign types. MUTCDs can be unified, but also on top of the MUTCDs, which is around maybe 200, 300 different sign types. There is also the state-specific signs in top of it, and also the resolution, the direction of the images could be also frontal, and also the GPS, the geo-tagged GPS information associated with those frames, they could be also has some errors as well. So what we did, we built a data set. That data set contains around 25,000 images, around 47,000 annotations, consist of 200 class labels. The good thing about our data set, it has the sign class, bounding box, GPS location. Each sign has its own ID and which side in the road it exists. And also, is it part of assembly of signs? I mean, assembly, is it part of one, like kind of physical, location for all the same signs that's been hanged on the same kind of metal hanger or not? And each image provide, the GPS. So the images that's been captured already provide the GPS and the camera heading as well. So we label this data and we convert to the other data sets existed in the field. So we have, as ours, we are kind of the most rich data set. We have 199 different type of signs compared to others. So this maybe I can tell the biggest public data sets already existed in the field with more than around 200 sign types. We have maybe number of images and number of annotations in here. So number of annotations is the highest across all the data sets, as well as we have the GPS being captured, and we have actually a very good resolution as well. So this is not just only what we have, but also during, let me run this as well. During when we captured the data, we captured also across years. So for example, like this one is 2019, this is 2020, this is 2021, this is 2022. For every single image in here, it's the same location, but at different years. So we captured also those signs across the years as well. So we can localize them not just only spatially, but also temporally across the years, which is kind of has a lot of interesting applications on how to track the sign health information and maintenance information over years as well. So this is the data set that has this kind of specific, property and feature that is different than other data sets. The way how we label the data, we used, we know that GPS information is not that really accurate from the given image in here. So we went to the sign and we also evaluate its location on the satellite image. We get the satellite GPS information and we capture this as our GPS information. That is how we build sort of kind of accurate, or almost close to accurate data set for the GPS location for the signs. Even it is actually comes from a noisy GPS frame, but at least the GPS information for the signs should be correct. The first thing to solve this kind of trying to localize the image, the signs on the map, start by the detection model. And detection model is just you can bring any detection from the shelf and you can use it. But there is actually something that we need to do and substantially change those detection models by introducing what we call the GPS head. This GPS head is trying to spit out the GPS location for every single sign in the frame that you are trying to detect the signs in. So it's not just going to tell you where this, what is the sign type and bounding box, but also where's this GPS information is. Surprisingly, those been working really well. even in just only one frontal images. Typically, we as a human, we use this kind of stereo vision to localize the object, but luckily those kind of detectors just only from one frame, one image, you can localize the object where it actually exists. This not just only at the beginning I was thinking maybe the sign size could be different and if it is close by and it's like far away, how you can know, but there is a visual information around it, like trees, roads, and so on. All this information will help in estimating the depth information from just only a singular, frame, which is really great. And the detector performance was actually doing really well. We have around roughly true positive 7,600, false positive around 1,800. And by the way, the false positives is something like I can tell the number is much less than this, but there is a lot of signs that's really far away, small signs that never been actually been labeled, but already existed in the data set. And we consider those as a false positive because it needs a lot of refinement for those signs to go and revisit the data set to label them again and again. We did this kind of iteration, but there's many false positives just come as they are true positives, but being detected as false positives. False negatives also is those detectors sometimes they miss one of those signs, especially if they are on the side far away. Those signs kind of really missed. GPS error was okay, 4.5 meter. That's actually also aligned with the GPS error already existed. Again, this solution or this technology that we are proposing in here just depend on the frontal images, and because we have the GPS error from the frame itself, we cannot just tell how much the error is cannot. It's going to be an ill-posed problem to exceed the GPS error already existed in the current images. If we connect it to the satellite, that could be a different story. So we can basically combine the two technologies that I described before with this one, and we can reach to a better, accuracies. Now, the technology, all this what we mentioned is not that really complicated. The one is complicated is what we call the tracker. Tracker is, suppose that you have two frames. This is the first frame and this is the second frame. And by the way, the images when it's captured at this resolution, for example, in here, and maybe after 8 or 10 feet, you capture another image. That is most of the transportation departments, they get those kind of temporal resolution is not going to be very high dense, because if you have kind of a video stream with a high frame rate per second or FPS, that will be really too much to keep such a high resolution data in the house of transportation departments. So what they do, every single maybe 8 feet or 10 feet, depends on the speed of the vehicle, they capture those kind of images and they keep them on their repositories and databases. But the issue is the information from this frame to this frame will distractly change. And also the other important problem is this sign is the same as this sign or not? Because you capture this frame, you find a sign. You capture this frame, you find another sign. Is this the same sign or not? Is this north and south is the same north and south? Or is this a new sign or not? So we need what we call a tracker that track this sign and find it is correspondent in the next frame. The problem is those kind of visual information drastically change because this is actually far in distance, because the resolution, the temporal resolution of the capturing is really kind of low and it's going to be difficult to capture those. So sometimes you find this sign, if it is really big on a highway, you can find 15 frames that shows on that sign is showing in 15 frames. But sometimes if it is a small on the side, maybe and on kind of a turn, it may be just shown one time. So that's actually make the problem of the tracker that we implement is super difficult and is not easy. So how to make sure that the same sign on frame one is actually if it appears in the second frame is going to be the same or not. So we are defined, kind of visual information that combines things. This sign is the same as this sign, this one is same as this one, and this one same as this one, and so on. And also we capture what we call positional encoding, the position and the class type on another set of maps, and try to do this kind of sort of association. After we building this kind of vector encoding for visual and positional information, we pass it to this distance metric network. We pass every single sign that's been detected from the detector, as well as like the positional encoding for each sign, and we pass it to a neural network and try to see how much it close this based on their visual information, based on positional information, and try to say this sign is the same as that sign or not. The third part of this algorithm, which we call Hungarian algorithm. Hungarian algorithm is trying to do association, which basically you have many signs in a frame 1 and you have many signs on a frame 2. Which one is associated to which? So this Hungarian algorithm is trying to find the best association between those. Giving that is not necessary to be the same number. It's not necessary to be actually, they could be actually totally different, signs, and the associations maybe not should not be associated from the first place. So this Hungarian algorithm is try to solve this kind of optimization problem, try to associate based on the distance metric, based on the visual information, and based on the historical information as well. We all engage on all of those in kind of complicated way in what we call the Hungarian plus algorithm. I don't want to go into these details, but that is kind of the main aspect. One more important also feature of our work, what we call temporal pairing. Like we can, transportation departments can collect data from multi-years. 2012, they can just go and scan all the images from the state. In 2013, they can repeat this step. 14 is going to repeat this step, and so on. The question would be, if you detect a certain object in 2012, can you find it in 2013? Can you find that the same object in 2013 and 14, and so on? So that is actually kind of the same association problem, but in sort of temporal aspect instead of spatial aspect. Instead of doing it in multi-frames, that's being captured in multi-frames, you can capture those in multi-frames and temporal way. And that is what also we've been doing. But we developed what we called windowed Hungarian matching to reduce this search, because if you have a certain sign live in somewhere in your data, to find where it is exists in another data set is actually takes a lot of time. So you need to find a way just to do this kind of matching on a subset of data, just only optimized technique to reduce the number of the calculations. But we use roughly the same algorithm with a distance metric that I described. Then, we used the question would be the initial question: why we don't use the other trackers? If we use the other trackers, actually our data set is going to fail miserably, because again, the frame rate, or the other trackers assume high frame rate. Our data set has a low frame rate, and that is not going to work except with this kind of specialized Hungarian algorithm and the specific, tracker specs that is different than other ones, especially with the distance metric that we built. Now, the results, we achieved actually kind of good results, not bad results. And it seems like, if I'm just gonna show the F1 scores is around roughly 90%. We just talk about the true positives and false positive and false negatives. We have true positives like kind of 66,000 roughly. We have false negative around 2,700 and false positive around 1,500. Roughly from the data that I have, maybe not in this slide, we have a recall about 92% with a precision around 83%. So if 92% of the signs has been detected, from those 83% has been accurate. Now, actually for those signs, they are close to the frame or close to the camera, they actually really being detected very well. Let me give you a demo here about the tracker performance. So this is the tracker. Now the color of that image, if it is, for example, like the certain color, if it is kept the same color, means it is the same sign that we are detecting it across multiple frames. For example, like this one is come the orange. If it's still the orange, it means that it's the same sign. This kind of color coding for the signs that's being tracked over time. Seems like to be working really well. All the signs has been tracked really well, and from every single tracking and detection, we average those GPS information and we spit the final results on the map. We have all of this in our paper called Object Tracking and Geolocalization from Street Images that's been published in 2023, I guess, 2022. And we have also a widget viewer, a solution that I can also go over a demo and explain this, our solution over the demo for you guys. First of all, we do a data storage. We implement also, so part of our solution in here is not just only just I do a theoretical research and show some numbers. We would like to show some demo. So we get from VTrans, we get around 6 years or 5 years, 2012, 13, 18, 19, 20, 21, and 2022. And we get all of those years for the data from all Vermont. Then what we did, we process all this data and spit out the signs. So, and this is actually part of what you see in here. This is the signs that is actually distributed across part of Vermont. If you zoom out more, you will see most of the signs in a whole Vermont state. Then you can just go and click at any image, and you can click at any sign as well, and you can visualize the signs as well as you can visualize the image. You can go as a navigator and you can just see the images after each other. You can see the signs as well, and you can click on the sign and you can see the property of that sign, what exactly the sign is for, and so on. And more interestingly, we do what we call multi-year tracking, which means like we can go to a sign that we know it is belonged for 2015 or 19, and then you can see it also belongs to 2000. This one, for example, this sign is seen in 2018, 19, and 2022. You can click on the year and you can see it in different years as well, which is really cool, which is really nice. This feature, we work on it for many, many months until we make it work. It's not easy to be implemented. And also, I will explain more about the demo in a second, but typically our demo is we have image viewer, we have those functional buttons. In general, here you can actually go scroll across the images. You can do the temporal selection for the years that you are looking for. You can do the bounding box. You can find the aerial images. You can add a user comments. You can just have interaction reports inside those kind of images. Then you can, if you click on a sign, you have the dialog for the traffic sign options, and you can see where they are located and so on. So all of this work has been licensed from my lab, and we have Maplyzer company that is already now launched, and they have customers, and we are doing some work, interesting work. This work is not just only for signs. We are scaling this for different features like safety features. We try to find, for example, like the clear zone, there's the guardrail, the sidewalks, the objects on the side of the road, and many of those kind of safety objects or safety measures on the road, and try to give a report where maybe a more safety measures needs to be done and implemented on the road to increase the safety of the streets. I will also more features about our technology can be easily customized for other DOTs. It's true that's been trained on VTrans, Vermont Transportation Department, but also can be easily, we can get data from other from other states, and we can automatically extract all of these signs. We have manual cleaning and labeling capabilities already because AI, even if it reached 90-95%, can you push it to a human level performance? That is what we have now, cleaning and labeling capabilities on the same solution that we have on the same widget, that to make it much faster and much easier. We are now working on other capabilities such as guardrail, wide sidewalk, as I mentioned, and safety zones and clear zone and so on. Please today, like if you have a comments or a nice solution that you would like to see for your transportation department, please let us know about those. Let me also, before we jump to questions, let me just, we have 3 minutes maybe, but I can go to Maplyzer, our demo, and I think you can see my, you can see can you see the window? Which window, Dr. Musa, you can see now? Is it the
We,
website?
yes, we just see the Maplyzer and then we see the start button.
Perfect. Okay, excellent. So that's our demo or our solution. Now the years will be loaded, all the layers from the years. Takes just a little bit to be loaded. Once it's loaded, we can select the year and we can start playing with things. I just want to give a very quick demo here about it. So just click, for example, like 2018 or 19. So you can basically zoom out. You can see all the images. It's being collected across Vermont in 2018. You can see the signs actually behind those kind of, in here, embedded in this location, for example. You can click at any image, for example, and those that are the images that we are clicking on. You can click on that image, for example, and you can basically see where this image has been located. It's located in multi-years, and you can click on that one, and you can see it. You can actually just go to it. That is the hospital, sign that been actually mentioned before. That's actually not the one. That's actually getting its edge. That is interesting to see. That's one of the error detections. This one should be getting it right. Okay, so as you could see, this is the sign for the crosswalk. And the crosswalk has been shown in 2019, 20, 21, 22, and you can track it over time as well. You can think of those as, like you can just go to all these kind of signs and try to see how accurate they are and so on. Again, the accuracy around 85%. We have been working on other technologies such as, for example, OCR, to recognize this kind of, for example, like this edge error. So this is not a hospital, as you maybe noticed, but how we can increase the accuracy for this. We've been actually doing some OCR technology for the signs and try to make sure that, for example, this is not the edge for hospital. This is the other, for example, like the other signs. If we have any other kind of text that's been written on those to have a better understanding of those kind of signs and types. I can You can play with this demo. It is in our maplyzer.com, and you can log in there. You can just see and play with those demos and see how could be interesting and so on. Sometimes what happens, maybe this could be an error. There's 3 signs like this in this location. They could be repetitive, could be not. They could be maybe multi signs in there, could be one sign and so on. But as mentioned before, those signs is already kind of this is kind of the sign that we are talking about. You see how small this sign is and it's been detected, and this is another sign in here. So these are 2 signs. It's been kind of detected correctly. The third one could be in wrong. So one in here, one in here, but this one could be actually not being tracked correctly. But at least this example is actually a good example how our algorithm is getting those kind of small signs, which is can be difficult and tracking them over time. Oh, by the way, this sign has been detected as the third yellow one, by the way. That is my assumption in here, and that we detect this as a sign as well. So those are correct, the three of them, but the GPS location is not very accurate in here. With that being said, I'm done with the demo, and I can go back to the slides. If you guys have any kind of sort of questions, I will be happy to answer those.
Thank you so much, Dr. Wshah. I really appreciate it. You are talking about very important topics, which is very really connected to what we're doing here at CINSER, especially when it comes to carnations, but not from the angle you're doing it. That you're opening my eyes on many problems. Thank you so much for what you shared and the informative comments that you presented to us today. I have several questions, but let me see if anybody in the audience has any questions.
Yes, I have a question.
Please go ahead.
Okay, so I came in on kind of the end of your presentation, but I wanted to know, what is this information useful for?
Yeah, thank you, Aisha. So for this information is helpful for transportation departments. This application specifically for the signs is important for transportation departments. One thing,
Okay.
what they do, I'll just give you an example. Suppose that you have a segment of a road that has some signs on it. That by federal law and state law, those signs needs to be maintained and replaced every maybe 10 years. Why? Because they have what they call one aspect and one reason why they need to be replaced. They have what they call retro reflectivity, which means like if you're driving the car in the night, the light that you show on that sign should be reflected. If it's not reflected, it's not going to be visible. So this needs to be replaced every 15 years or 10 years, depends on the federal and the state laws and based on the location of the sign and the type of the sign. So it needs to be tracked. The only solution now, they track it over time by manual people. They go down the road and they just start to say this sign in this location, this type is has been installed in this time, and they just track it this way. That's too much costly, and human can make mistakes and so on. So can be done automatically from the data has been collected from transportation departments themselves. Or can you drive a car with the dash cam and just collect all this data and track those signs every year and say this sign has been, this is, we localize the sign, we identify the sign, and this sign has been installed this time and never been replaced, but this year has been replaced. So you can track it and you can localize it on the map. Yeah. But that is one aspect of the reasons, or this is one reason why it needs to be tracked. But there's also other reasons as well. Yeah. Great question, Ish. Thank you.
Another question. Safwan, Dr. Wshah, I'm interested to learn more about the scalability of the system. Basically, now we're talking about Vermont and collecting the data in the city of Vermont. How scalable is the solution to other cities?
That's
And
actually a great question, Dr. Musa, because most of the AI systems now, they struggle with scalability, as we know. The question would be, if I want to take it to another state, how we can make it to work. As a product, and I can answer this question in two aspects or two type of answers. As a product, we can go to a new state. We can roughly get a data 5% or 1%, and we can manually label those after being processed by AI. So AI maybe get 70% or 80% accuracy. Can we correct those by our human labeling? We already have this feature. Then fine tune it, then apply it again another 5% until we see the model to start to, uh, you know, um, be to the new state. That is kind of one model. Science-wise, the good thing about Vermont and maybe for most of other states, he used what we call MUTCDs. MUTCD is the the same type of signs they used in this state and maybe another 39 states. They used MUTCDs. So it's easy to scale the system that we implemented for the signs because we are follow the MUTCD kind of conventions and the Vermont states they use this MUTC, which is easily to scale to another states. So science-wise also, we can implement those algorithms and better trackers for scalability. As we go from one state to another state to another state, you can build this kind of general, sign recognition system that hopefully can be better. Another things that to solve it, you can think of unsupervised machine learning algorithms, how you can get data not labeled from multi-states and easily you can find this data. It's already existed publicly. And just you can train your model to shift the domain from one state to another state based on this unsupervised data. That's another way of looking at it. But all of those, they need babysitting. We have a vision to implement something like a global solution using VLMs, what we call vision language models. Hopefully they can trained on a big high scale of information and can answer all this kind of scalability problem. That is something that we are working on, but still in the very early stages.
Okay, thank you. Because you're taking make a next question about how the performance of such systems and AI-powered solutions in areas in ultra-dense environments. And like in cities are really, really dense and where you have all these signs, quality of signs are really sometimes are not the best. I don't know, but maybe I'm sure
Yeah.
you.
Yeah, absolutely. That is going to be a problem, right? So because in luckily Vermont does not have that really too much urban areas. I'm not sure if you know Vermont, but if you think about Burlington area, we don't have that really big buildings and so on. You can think of it as like a small towns in big states. You can think it this way. But if you go and drive in Chicago, it is tons of signs in the roads, right? Especially in the downtown. How you can keep up and how you can just do this kind of association between the signs and keep a track for those. That is a very challenging problem, I can tell. Now, and their solution is the current AI systems can solve this problem. For now, I can tell maybe not, but there's needs to collect data, especially from those urban regions, and try to make sure that the system is well defined for those urban contexts before taking it to this kind of regions. But I can tell those regions could be manually taken care of. But the problem is about 80% or 90% of the roads they already not maintained. Like in small urban, highly dense regions, a human can control those, but outside it's going to be really difficult to control those. And that's where actually the need for those transportation departments. Their needs all the time when they define for rural areas where driving the cars on high speed, whereas kind of the safety measures is really important for them. They need those signs to increase the safety of the roads and so on. So they care more about highly dense urban areas, and they just go to those kind of urban, rural areas and other type of roads.
Oh yeah, absolutely. Any other question from the audience? Because I have one question connected to the public safety aspect. I'm not sure if you agree with me about that. I see a very good application for such work when it comes to um, enhancing public safety from a perspective of disaster response and emergency services. I'm not sure if you looked at it from this angle also, because I see this kind of a great impact on our public safety.
Absolutely. So this technology that we are again about geospatial understanding. Just think about one thing. Actually, there is a project that we are applying for called video links. And let me explain a little bit about it. So in video links, which is a public safety, suppose there is someone you would like to track someone on the road, saying that person, that car is moving from this camera to that camera and to that camera. Can you localize the object? Can we're localizing signs in here, right? But can you localize a car? Not just and it is a moving object, but you have a stationary camera. So a problem is opposite. But you try to track a car, to localize a car from one camera to another camera to another camera. So there is localization, there is tracking as well. So this actually we submitted our proposal to that project, which is basically is a public safety. Can you track a car or a human in multi kind of cameras, and you can track those over time, and you can localize it on the map, and you can say that person or that car existed on this this location on this map, and people can track it. That is actually very important for the public safety. That's one aspect for the public safety, Dr. Musa. But there's other public safety important things. For example, like localizing someone just like in a forest area and they are lost, and they really don't know where they are, and try to describe where they are, and there is no GPS information and so on, how they can describe. So all of this kind of information is also public safety is important as well from that perspective.
But you mentioned the GPS uncertainty in the beginning. Do you see it? Did you see this work kind of a way to augment GPS let me say in GPS denied environments or GPS challenged environments where this work can really complement or augment GPS?
Yes, it might be. Like there is definitely this field of the computer vision trying to define the GPS information and GPS denial areas is very important. So this might work in the future. For example, like when those cars is being driving autonomously, suppose that GPS information sometimes because a war happens, someone just like maybe cut all this light information right on you. So what are you going to do? All autonomous vehicles will crash. So can you just have a better system to localize where you are and so on? So all of those kind of information about localization can work as alternative definitely at some point.
And if any other questions, I see there are some comments there in the chat. I see there's a comment from Isha, which is saying she's thinking this technology is very important for our safety. I don't know if there is, but I maybe there's a one burning question. I cannot be like one of the leads of our Center of Security here in Chicago State without asking it. Are there any safeguards as far as security and privacy, especially when talking about surveillance and collecting all this data about all these roads and all these spaces? And as far as when you collect all this data and you do build all these data sets, how much safeguard, what safeguards that you are keeping in mind when you're dealing with this data from our security and privacy?
Can you come again, Dr. Musa?
Question is how you're collecting a lot of data, and this data, by the way, it's a kind of surveillance about our streets and our signs. How much do you have any safeguards to protect our data or to keep them in mind as you are building your algorithms and dealing with these data sets?
Yeah, that's a good question, Dr. Musa. And let me just give you a little. So, because you are center of security, right? And
Yeah.
privacy. And let me mention this. We've been talking about having a GPS localizer using a vision information. Imagine this, Dr. Musa, that you have a model, you give it an input vision information, it's going to tell you where the location is.
Mhm.
That is a global model. Suppose that we reach to this theoretically, we reach to, or hypothetically, we reach to that global model that can answer this question. That is a disaster if it's not protected, because someone can hack that model, can give you a satellite image for army station, and can give you all the ground images for that army station. Because that model, what's the task for that model is to provide a ground image and find that corresponding satellite image. Can you hack it in another way? You get satellite image and you find the ground image. That is possible. That's very possible because you can, as I mentioned in some point in that, you can provide, you can generate from ground image the satellite image, and you can generate from satellite image the ground image, and so on. How to protect this? How to secure it? That's actually a big question, big open question needs to be answered. Okay. I'm happy to cooperate with you guys on this at some point if we need. But such kind of foundational models, such as cross-view geolocalization models, how to protect them, how to make them private, not to extract private information, secure them, all of those kind of really important to work on, especially Dr. Musa, what we call the cross-view, which is multi-view, which is multi-modalities. The question would be in cybersecurity and privacy, is there enough research in differential privacy that work on multimodalities? I don't think much, and that could be an open research area, right, for to browse in the future.
Thank you so much. I think maybe I see Lizette just put her image there. Do you have any question? Or okay. Again, we are towards the end of the webinar. I really appreciate your time, Dr. Wshah, and the insight you shared with us today in this CINSER webinar. And again, on behalf of Chicago State University and our Center for Information Security Education Research, CINSER, we're really thankful for your presence and your time. I knew you just came from travel and you dedicated, you can give us this time for today. I really appreciate it. And looking forward to connecting with you in the near future.
Absolutely. Thank you, Dr. Musa, for inviting me. It was a great pleasure to talk to you, everyone. And please, if you have any question, just shoot me an email and I will be happy to answer it. Thank you. Thanks again.
Thank you so much.
Bye-bye.